the value of dk by ds equal to 0, the equation we got it as minus of 3s square plus 8s plus 13 equal to 0. So we can take off this minus. Now we need to find the roots for s. Roots for s are minus b plus or minus square root of b square minus 4ac. A is 3, c is 13, 4ac by 2a. So if you solve this, you get it as 1.33 plus or minus j 1.6. So once you get this value of s, it is the roots for dk by ds equal to 0 equation. We need to check the value of k, for which value of s k should be positive and real. K should be a positive value and real value. So for that value of k, we need to find with respect to s. So here k equation is there. K equation is s minus of s cube plus 4s square plus 13s. Let us first take the value of s as minus 1.33 plus j 1.6. If you substitute the value of s in place of s in the equation, since it is a complex value, definitely the value of k won't be real. So you don't get a real value. So s equal to minus 1.33 plus j 1.6 cannot be a breakaway point or break-in point. So s is equal to minus 1.33 plus j 1.6 is not a breakaway or break-in. The reason is, for any value of these complex numbers, complex conjugate numbers, plus or minus j 1.6 for this one, we don't get the value of k as positive value. It may be a positive, we don't bother about it, but it won't be a real value. So real value won't be obtained. So calculating the value of k for this s equal to 1.33 plus j 1.6 is waste of time, since you don't get any positive value or you don't get any real value here. So straight away we can say there won't be no breakaway or break-in points. So breakaway, break-in won't be there. And by seeing the structure of the root locus, we can easily guess it. Since we have only complex conjugate poles, they give us only angle of departures. So breakaway, break-in will come if we have two poles on the real axis. Since we don't have two poles on the real axis, we don't get breakaway, break-in. So anyhow, this is the method to find how to get the breakaway, break-in points. So if we have two poles, breakaway will come. If you have two zeros, break-in will come. So find the the derivative of k, dk by ds equal to 0, and substitute the value of s in the k equation. So if you get real and positive, then we say there will be breakaway, break-in. So let us go to the next step. Step 5. Step 5 is to find the angle of departure. To find the angle of departure. So as we already understood, we have complex conjugate poles. So definitely we will have angle of departure. So for that, we saw the procedure to find the angle of departure. I am roughly drawing the method here. So it is sigma and it is j omega. We have two complex conjugate poles. One is at minus 2 plus j3 and the other one is at minus 2 minus j3. So as we saw the procedure, we need to draw the vectors. We need to draw the vectors from these two, and we have to find the angles here. let it be the angle theta 1 and let the angle this one be theta 2. So obviously theta 2 is 90 degrees, we can understand it. And to find theta 1, if you don't have protractor, we can follow this method. This length from here to here is 2, that we know, and this opposite side is 3. So theta 1 can be find theta 1 can be obtained by this method, 180 degrees minus tan inverse opposite by adjacent 3 by 2. So if you calculate it, you get it around 123.7 degrees. And theta 2 is obvious, it is 90 degrees. So once you find all these 2 degrees, the angles, angle of departure can be obtained as, so let it be P2 and let it be P1, pole 1, pole 2, whatever be the way you take it. So angle of departure P2 will be 180 degrees minus theta 1 plus theta 2. So 180 degrees minus theta 1, one angle is 123.7, the other angle is 90 degrees. So sum it and subtract it with 180, you will get it around 33.7 degrees. So this is the angle of departure at P2. So angle of departure at P2 will be, with reference to this, we have to take this angle as 33.3 degrees. So it will be 33.7 degrees, sorry, and it is a negative angle. And the angle of departure at P1 will be negative of the angle of departure at P2. So it will be plus 33.7 degrees. So whatever we got it in this one, the same angle will be there, but with a sign change. So these two are obtained now. Now let us move to step 6. Step 6, we need to find the crashing point on imaginary axis. So if you want to complete the root locus, if you roughly draw the root locus, it is like this. We have sigma here and we have j omega here. And what are the points we found so far are, we know these poles we know, and we have centroid. Centroid is 1.3 around, and from this we found the angle of asymptotes. Once you got the angle of asymptotes, we just found the angle of departure. One is at minus 33.7 degrees, the other one is at positive 33.7 degrees. So they move from these angles like this. With reference to this one, it will be like this, positive 33, and with reference to this, it will be negative 33, and they have to meet 0 at infinite. So we have to find at what point the negative axis is being crashed. Anyway, this pole is going to infinite here to meet 0. So these things we need to find. So crashing point are to be found now. So for this one, we have the characteristic equation, s cube plus 4s square plus 13s plus k equal to 0. From this characteristic equation, the best way of finding the crossover is to substitute s is equal to j omega. If you substitute s equal to j omega, we get j omega whole cube plus 4 j omega whole square plus 13 j omega plus k equal to 0. So from this, just simplify it further, j omega cube minus we get it as 4 omega square plus 13 j omega plus k equal to 0. So let us take out the imaginary parts aside and imaginary one side and real on the other side. Imaginary we have minus j omega cube plus 13 j omega, let it be equal to 0. The real parts are minus 4 omega square plus k equal to 0. So if you simplify this one, we get it like the real part, okay, the imaginary part 13 omega is 0. So take out one omega from this one and write the expression for omega square. It will be 13, and we have omega square here minus 4 omega square is 13 plus k equal to 0. From this equation we substituted the value of omega square as 13 and the value of k is 52. 4 into 13, that is 52. So now we got the crossover point from here. What is the crossover point? Omega square is 13, omega is plus or minus square root of 13. Square root of 13 will be plus or minus 3.6. So 3.6 on imaginary axis, the value of omega, it is an imaginary value, that j omega. So 3.6 plus and minus will be the value of this point, plus 3.6 on the imaginary axis and minus j 3.6 at this point. These two are the meeting points or crossover points of the root locus on the imaginary axis. And at these crossover points, the value of k, at these crossover points, the value of k is equal to 52. That is what we obtained from this diagram, from this calculation. So let us indicate 3.6 on the root locus on the graph. So our graph is here and 3 is here, 3.5 and 3.6. It will be somewhere here. 3.6, let me note the value, and it is 3.5 and it is, let it be minus j 3.6. It is also the imaginary value j 3.6. So we found the angle of departure from this reference. From this reference we need to find the angle of departure as 33.7 minus. So let it be like this, that comes in this way, 33.7, and from this reference we have 33.7 positive, so that will be in this way. So 33.7 here, and these two branches will start with this angle and they have to meet the imaginary axis at 3.6. So we can write like this, it is moving in this direction and that has to take the diversion here, and that goes in this way, and here also it is moving in this direction, it is moving in this direction with 33.7 degrees, and that has to go in this direction touching 3.6 on imaginary axis. So these are the final plots that we obtained, and at this location the value of k is equal to 52. It is a maximum value of k. So the angle at which these branches, the angle at which these branches will go towards the infinity is along the asymptotes direction. So asymptotes along 60 direction, they will move in this way. Here also it moves in this way. So finally the graph will be like this. So 60 degrees will be in this direction actually. So it is how the root locus will move towards infinite. So it is a graph which resembles the actual one, and plotting the actual graph from this sheet is not possible in fact. So you just take the values that we have taken and construct as per the values that are obtained in the calculation. So let me quickly refresh you how we have plotted it from the point 1 to the last point. So we were given with the open loop transfer function. It is a given open loop transfer function, and this open loop transfer function, we found the loop transfer function. Since h of s is equal to 1, the loop transfer function is as it is in the given problem, and we have the characteristic equation. We first identified the location of poles and zeros. One pole is at the origin, and we got two complex conjugate poles. Since we have complex conjugate poles, we have this angle of departures that we need to understand first. And from step 2, we identified the portion where we have the real axis on root locus. Since we have one odd pole at the origin, the entire root locus, the entire negative real axis is on the root locus segment. And then in step 3, we found the asymptotes. Asymptotes are the angles at which the root locus branches will go to infinite. So we got three values which are standard: plus 60 degrees, minus 60 degrees, and plus or minus 180. Plus or minus 180 degrees will indicate the negative real axis, and we have to plot plus 60 and minus 60 with reference to the centroid. Centroid is calculated with this formula, and we got it as minus 1.33. Once you got centroid, step 4 for this problem can be avoided, but for your understanding, I explained you how to find the breakaway and break-in points. We have to find first the closed loop transfer function. From the closed loop transfer function, we need to get the equation of characteristic value with k equal to. Then we need to find the derivative of k, dk by ds, and that has to be equal to 0, that is to be made equal to 0. And we need to find the roots of s and substitute the roots of s in k equation. If you get positive and real value of k is the open loop gain. In fact, since it is open loop gain, it takes only positive and real values. It must be a positive and real value. Since we have s as a complex conjugate, and substituting complex conjugate in k equation won't give us real and positive value, we definitely don't have any breakaway and break-in in this case. And then the next step is to find out the angle of departure. Angle of departure is obtained with the formula 180 degrees minus theta 1 plus theta 2. These are the angles corresponding to each pole towards the required pole where we need to find the angle of departure. So it is the targeted pole P2. We have drawn these two, and from this we found the angles theta 1, theta 2, and we added it, and finally we got it as minus 33.7 degrees. Once you get one complex pole's angle of departure, the other complex pole's angle of departure is the negative of that one. So it became plus 33.7 degrees. And finally, we found all the values. We found the asymptotes, angle of asymptotes, and we found the centroid, and we got the angle of departure. And finally, if it has to move towards infinite, we need to get the angle, the point at which it crosses the imaginary axis. To find that one, we substituted the value of s is equal to j omega, and we found the value of omega as plus or minus 3.6, and with the value of omega we obtained the value of k as 52, and we plotted all these things on the graph, and finally the graph obtained is something like this. So if you take the actual readings on a plane graph with all the protractor and all, you will get a clarified with a clarity diagram. So it is only for your reference. This diagram that we have seen here is only for reference. So you try plotting the same method on a real graph with the angles measured properly. Thank you.